So welcome to Artificial Intelligence for Robotics. You are entering an exciting 7 weeks class in which you learn how to program self-driving cars. And just to motivate what we're trying to achieve in this class, let me show you some videos. So my interest in self-driving cars started with the DARPA Grand Challenge in 2004, in which my team at Stanford developed Stanley, a robot that could drive itself through the Mojave Desert. The vehicle was based on a Volkswagen Touareg. It was equipped with all kinds of sensors like GPS and laser, and it was able to make its own decisions without any human input whatsoever. The DARPA Grand Challenge was a government-sponsored race that took place in 2005. Here we see our robot Stanley moving through the desert completely without a human on board. The task was to drive a desert trail for about 130 miles, and whoever was fastest would win the race. Here we're passing a different robot by Carnegie Mellon University about 110 miles into the race. Our robot was able to navigate really steep mountainous roads and able to avoid collisions with rocks or falling down a cliff, all based on its ability to use what I'm going to teach you in this class. After almost 7 hours and 131 miles, our robot returned all the way to the starting base as the first robot to ever finish a DARPA Grand Challenge, winning Stanford University $2 million and Stanley a place in the Smithsonian Museum of American History. This work led to the Urban Challenge, in which we built another robot called Junior that eventually took second place. The Urban Challenge was a follow-up race by DARPA in which cars were asked to drive in traffic. So whereas the Grand Challenge was kind of a motionless desert floor, this was a mock urban city where the robot was able to interact with other traffic and had to follow traffic rules, as in this left turn over here. It had to be able to stay on lanes with very high precision, accommodate oncoming traffic, and just drive confidently in a situation that really resembled a small city. This led at Google to a sequence of experiments known as the Google self-driving car, and I believe these are the best robotic cars out there today. Here we see one of our Priuses on University Avenue in Palo Alto, kind of undetected, driving just like a human driver, but this car is driving by itself. Our cars have been able to drive hundreds of thousands of miles all across California and some of Nevada, in downtown areas like San Francisco, on busy highways, here in Monterey, a small coastal city in California with lots and lots of pedestrians. And these are all completely self-driving moments where the car is able to accommodate things like deers in the headlight in the middle of the night, or even crooked Lombard Street in San Francisco, as shown in this video. This is what I'm doing on my day job. I really love, with my team, building self-driving cars. We believe it's going to really change the world. And in this class, that's what I hope to enable you to do. So let's dive in.
Hello, I'm David Silver, the head of Udacity's Self-Driving Car Engineer Nanodegree program. This program prepares students like you for jobs as autonomous vehicle engineers. The Nanodegree program is a more rigorous and cutting-edge version of this free course. Sebastian first recorded this free course back in 2012. It was one of Udacity's first classes, and it is amazing. This was the first course that I took when I was learning to become a self-driving car engineer. Everything Sebastian teaches here in AI for Robotics is worth learning. But if you're really serious about learning how to program self-driving cars and become a self-driving car engineer, there's much more you'll need to learn. Not only will you need what Sebastian teaches here, you'll need to study deep learning, computer vision, motion planning, and system integration to go even further. The best way to learn to program autonomous vehicles is to join the Udacity Self-Driving Car Engineer Nanodegree program. Hope to see you there.
The very first problem I'm trying to solve is called localization. And it involves a robot that's lost in space. It could be a car, it could be a mobile robot. So here's his environment. and the poor robot has no clue where it is. Similarly, we might have a car driving on a highway, and this car would like to know where it is. Is it inside the lane or is it crossing lane markers? Now, the traditional way to solve this problem uses satellites, and these satellites emit signals that the car can perceive. That's known as GPS, short for Global Positioning System, and it's what you have in your dashboard if you have a car with GPS that shows you the maps and shows you where you are. Now, unfortunately, the problem with GPS is it's really not very accurate. It's really common for a car to believe to be here, but it has 2 all the way up to 10 meters of error. So if you try to stay in the lane with 10 meters of error, you're far off and you're driving right over here and you crash. So for our self-driving cars to be able to stay in lanes using localization, we need something like 2 to 10 centimeters of error. And then we can drive with GPS in lanes. So the question is, how can we know where we are with 10 centimeter accuracy? That's the localization question. In the Google self-driving car, localization plays a key role. We record images of the road surface and then use the techniques I'm just about to teach you to find out exactly where the robot is. And it does so with a few centimeter accuracy, and that makes it possible to stay inside the lane even if the lane markers are missing. So localization has a lot of math. But before I dive into mathematical detail, I want to give you an intuition for the basic principles. I want to tell you the story of how a robot localizes, and then we can go through the math together so you can understand it. I also want to let you program your own localizer so you can program a self-driving car. Let me begin my story in a world where a robot resides, and let's assume the robot has no clue where it is. Then we will model this with a function that I'm going to draw into this diagram over here, where the vertical axis is the probability for any location in this world, and the horizontal axis corresponds to all the places in this one-dimensional world. The way I'm going to model the robot's current belief about where it might be, its confusion, is by a uniform function that assigns equal weight to every possible place in this world. That is the state of maximum confusion. Now, to localize, the world has to have some distinctive features. So let's assume there's 3 different landmarks in the world. There's a door over here, there's a door over here, and a third one way back here. And for the sake of the argument, let's assume they all look alike, so they're not distinguishable, but you can distinguish the door from the non-door area, from the wall. Now let's see how the robot can localize itself by assuming it senses that it's standing right next to a door. So all it knows now that it's located likely next to a door. How will this affect our belief? Here's the critical step for localization. If you understand this step, you understand localization. The measurement of a door transforms our belief function, defined over possible locations, to a new function that looks pretty much like this. For the 3 locations adjacent to doors, we now have an increased belief of being there, whereas all the other locations have a decreased belief. This is a probability distribution that assigns higher probability for being next to a door, and it's called the posterior belief, where the word posterior means it's after a measurement has been taken. Now, the key aspects of this belief is that we still don't know where we are. There's 3 possible door locations, and in fact, it might be that the sensors were erroneous and we accidentally saw a door where there is none. So there's still a residual probability of being at these places over here. But these 3 bumps together really express our current best belief of where we are. This representation is absolutely core to probability and to mobile robot localization. Now let's assume the robot moves. Say it moves to the right by a certain distance. Then we can shift the belief according to the motion. And the way this might look like is about like this. So this bump over here made it to here. This guy went over here, and this guy over here. Obviously, this is a robot, it knows its heading direction. It's moving to the right in this example. But it knows roughly how far it moved. Now, robot motion is somewhat uncertain. we can never be certain where the robot moved. So these things will be a little bit flatter than these guys over here. The process of moving those beliefs to the right side is technically called a convolution. And let's now assume the robot senses again. And for the sake of the argument, let's assume it sees itself right next to a door again. So the measurement is the same as before. Now the most amazing thing happens. We end up multiplying our belief, which is now prior to the second measurement, with a function that looks very much like this one over here, which has a peak at each door. And out comes a belief that looks like the following. There's a couple of minor bumps, but the only really big bump is this one over here. This one corresponds to this guy over here in the prior. And it's the only place in this prior that really corresponds to the measurement of a door, whereas all the other places of doors have a low prior belief. So as a result, this function is really interesting. It's a distribution that focuses most of its weight onto the correct hypothesis of the robot being in the second door. And it provides very little belief to places far away from doors. At this point, our robot has localized itself. If you understood this, you understand probability and you understand localization. So congratulations. You understand probability and localization. You might not know yet, but that's really a core aspect of understanding a whole bunch of things I'm going to teach you in the class today. So let's move into our first programming exercise and let's program together the very first version of robot localization. So here's a bit of program code, an empty list. And what I'd like you to program is a world with 5 different cells or places where each cell has the same probability that the robot might be in that cell. So probabilities add up to 1. Here's a simple quiz for the cells x1 all the way to x5. What is the probability of any of those x's? So index I goes from 1 to 5. And the answer is 0.2, which is 1, the total probability, divided by 5 grid cells. So in our Python interface, I'd like you to take this code over here, which assigns to P an empty list, and modify it into code where P becomes a uniform distribution over 5 grid cells, as expressed in a vector of 5 probabilities. So here's an easy solution. You just initialize the vector with 5 0.2s. Let's see if we can modify this to make a vector of length n, where I can vary the value of n and get a resulting vector with n elements. So for n equals 5, we would get the same result as before, but for n equals 10, I should get a vector of length 10, each of which would have value of 0.1. And the answer is simple. You use a for loop, as shown here, and you append to the list n elements, each of size 1 over n. The dot over here is really important. It gives you the floating point version. So now we're able to initialize the initial belief of the robot in the world over here. So let's look at the measurement of this robot in its world with 5 different grid cells, x1 through x5. Let's assume 2 of those cells are colored red, whereas the other 3 are green. As before, we assign uniform probability to each cell of 0.2, and our robot is now allowed to sense. And what it sees is a red color. How will this affect my belief over different places? Obviously, the ones for x2 and x3 should go up, and the ones for x1, x4, and x5 should go down. So I'm going to now tell you how to incorporate this measurement into our belief with a very simple rule, a product. Any cell where the color is correct, any of the red cells, will be multiplied with a relatively large number, say 0.6. That feels small, but as we'll see later, it's actually a large number. Whereas all the green cells will be multiplied with 0.2. If we look at the ratio of those, then it seems about 3 times as likely to be in a red cell than it is to be in a green cell, because 0.6 is 3 times larger than 0.2. Now let's do the multiplication. For each of those 5 cells, can you tell me what the result would be multiplying in the measurement in the way I've stated. So please, for these 5 boxes, fill out the number. And the answer is obviously for the red cells, we get a 0.12, whereas for the green cells, we get a 0.04, which is the product of 0.2 times 0.6 versus 0.2 times 0.2. And this is in principle our next belief. It only has one problem, which is it isn't a valid probability distribution. And the reason why is probability distributions always have to add up to 1. So if I ask you what's the sum of all these values, then we find out it doesn't add up to 1. So please type in the sum of all these values. So if you add up all these values, you get 0.36. To turn this back into a probability distribution, we will now divide each of these numbers by 0.36. Put differently, we normalize. So please, in these 5 fields, enter your result for dividing 0.04 or 0.12 by 0.36. And please check that the sum of those truly adds up to 1. So 0.12 divided by 0.36 is the same as 12 divided by 36 is the same as a third, or 0.333. And 0.04 divided by 36 is the same as 4 divided by 36. That is 1/9. And if you look at these numbers, a third plus 3/9 is another third, gives exactly 1. So this is a probability distribution, which is often written in the following way. Probability of each cell, I, where I could range from 1 to 5, after we've seen our measurement, Z. The probabilist would also call it posterior distribution of place xi given measurement Z. So let's implement all this. So here's our initial distribution again. Here's our factor for getting the color right, or for getting it wrong. And let's first start with the non-normalized version. Write a piece of code that outputs P after multiplying in P hit and P miss at the corresponding places. So one way to do this is to go explicitly through all these 5 different cases from 0 to 4 and multiply in manually the miss or hit case. This is not particularly elegant, but it does the job. And as I hit the run button, we get the correct answer that's not normalized. And my next question, can you print out the sum of those to normalize them? Modify the program so you get the sum of all the p's. Well, it turns out Python gives you a function called sum. And if you now hit the run button, you get the correct answer. I want to make this a little bit more beautiful. I will introduce a variable called world. And for each of the 5 grid cells, world specifies the color of the cell. Green, red, red, green, green. And further, I define the measurement Z to be red. Can you define a function called sense, which is the measurement update, which takes as input the initial distribution P and the measurement Z and all the other global variables, and outputs a normalized distribution called Q, in which Q reflects the non-normalized product of our input probability, which will be 0.2 and so on, and the corresponding P hit or P miss in accordance to whether these colors over here agree or disagree. So when I call sense P, Z, I expect to get the same vector as output as before, but now in the form of a function. The reason why I'd like to have a function here is because later on, as we build our localizer, we will apply this to every single measurement over and over again. So this function should really respond to any arbitrary P and an arbitrary Z, either red or green, and give me the non-normalized Q, which gives me the vector 0.04, 0.12, and so on and so on. So here's my solution. I start with an empty list over here, and I build it up using the append command over time. And I do so by iterating over all the elements in my input probability P. And I set a binary flag whether my measurement that I received is the same I would expect at the ith grid cell over here from this list over there. And if that's the case, hit is positive, it's true. So we're going to multiply P with P hit. And if it's false, then the flag hit will evaluate to 0. 1 minus hit will be 1. So you're going to multiply Pi with P miss. I build up the list, return it, and run it. and out comes 0.04, 0.12, 0.04, and 0.04 as expected. So let's take that same piece of code and modify it to give me a valid probability distribution. Please modify this code so it normalizes the output of the function sense so it adds up to 1. And here are the 3 lines of code I used to program this in. First I compute the sum over vector q using the function sum, which makes it really easy. And then I go through all the elements in q and just divide it by s, which is the normalization. And when I run it, I get a ninth, a third, a ninth, and a ninth. So I've just implemented the absolute key function of localization, which is called the measurement update. Let's just go back to our example and see what an amazing thing you've just programmed. We had a uniform distribution over places. Each place had a probability of 0.2. And then you wrote a piece of code that used the measurement to turn this prior into a posterior, in which the probability of the 2 red cells was a factor of 3 larger than the posterior of the green cells. You've done exactly what I gave you intuitively in the beginning as the secret of localization. You manipulated a probability distribution over places into a new one by incorporating the measurement. In fact, let's go back to our code and test in your code whether we get a good result when we replace our measurement red by green. So please type green into your measurement variable and rerun your code to see if you get the correct result. So I'm now replacing the red by green over here, and I rerun my code, and out come these funny numbers, which is somewhere in there is the division by 44. But you can see that the first, the fourth, and the fifth grid cell have a much larger value than the grid cells in the middle. So let's dive in. In fact, I'd like you to modify this code a little bit more in a way that we have multiple measurements. So instead of z, we're going to make a measurement vector called measurements. And I'm going to assume we're going to first sense red and then green. Can you modify the code so it updates the probability twice and it gives me the posterior after both of these measurements are incorporated? In fact, can you modify it in a way that any sequence of measurements can be processed of any length? And the modification is simple. We will call the procedure sense multiple times. In fact, as often as we have measurements, which is the for loop over here, we grab the kth measurement element and apply it to the current belief, and then recursively update that belief into itself. In this case, we run it twice, we print the output, and for this specific example, we get back the uniform distribution. These are all 0.2s, approximately. And the reason is we up multiplied each field once with a 0.6 and down multiplied with a 0.2, and these effects were in total the same for each cell. And as a result, we get the same output over here. It's quite remarkable. So before we're done with localization, I'd like to talk about robot motion. Suppose we have a distribution over those cells, such as this one, a ninth, a third, a ninth, a ninth. And even though we don't know where the robot is, the robot moves, and it moves to the right. In effect, the way we're going to program is that we assume the world is cyclic. So if it drops off the rightmost cell, it finds itself in the leftmost cell. Suppose we know for a fact the robot moved exactly 1 grid cell to the right, including the cyclic motion. Can you tell me for all these 5 values what the posterior probability is after that motion? And the answer is all of these are shifted to the right. So the ninth and the leftmost cell comes over here, the third over here, and finally the rightmost ninth finds itself on the left side. So in the case of exact motion, we have a perfect robot. We just shift the probabilities by the actual robot motion. Now that's a degenerate case, but it's a good one to program first. Let's program this one. I'll define a function move with an input distribution p and a motion number u, where u is the number of grid cells that the robot is moving to the right or to the left. And I want you to program a function that returns the new distribution q after the move, where if u equals 0, q is the same as p. If u equals 1, all the values are cyclically shifted to the right by 1. If u equals 3, they're cyclically shifted to the right by 3. If u equals -1, they're cyclically shifted to the left. So please call the function with argument p and a shift to the right by 1. I've commented out my measurement part because for now I just don't want to do measurement updates. In addition to this, I will use a very simple P that has a 1 at the second position and zeros elsewhere. Otherwise, if we were to use the uniform P, we couldn't even see the effect of the motion, whether it's programmed correctly or not. And here's the solution. We start with the empty list. We go through all the elements in P. And this is the tricky line. We will construct Q element by element by accessing the corresponding P. And P is shifted by U. And if this shift exceeds the range of P on the left, we apply the modal operator with the number of states as an argument. In this case, it will be 5. Now, the reason why there's a minus sign is tricky. To shift the distribution to the right, U equals 1, we need to find in P the element one place to the left. So rather than shifting P to the right directly, what I've done is I've constructed Q by searching for where the robot might have come from. And that's, of course, in hindsight, from the left. Therefore, there's a minus sign over here. So think about this. This is a little bit non-trivial, but it's going to be important as we go forward and define probabilistic convolution and generalize this to the noisy case. So let's talk about inaccurate robot motion. We are again given 5 grid cells. And let's assume a robot executes its action with high probability correctly, say 0.8, but with 0.1 chance, it finds itself short of the intended action. And yet another 1.1 probability, it finds itself overshooting its target. You can define the same for other U values. Say U equals 1. Then with 0.8 chance, it would end up over here. 0.1, it stays in the same element. In 0.1, it hops 2 elements ahead. Now this is a model of inaccurate robot motion. This robot attempts to go U grid cells, but occasionally falls short of its goal or overshoots. And that's a more common case. Robots, as they move, accrue uncertainty. And it's really important to model this because this is the primary reason why localization is hard, because robots are not very accurate. So we're now going to look into this first from the mathematical side. I will be giving you a prior distribution, and we're going to be using the value U equals 2. And for the motion model that shifts the robot exactly 2 steps, we believe there's a 0.8 chance. And we assign a 0.1 to the cases where the robot over or undershoots by exactly 1. That's kind of written by this formula over here, where the 2 gets a 0.8 probability, the 1 and the 3 end up with a 0.1 probability. So I'm going to ask you now, for the initial distribution that I'm writing up here, can you give me the distribution after the motion? And the answer is, for our intended field over here, it's 0.8. The 2 neighbors 0.1, and it's 0 and 0 over here. Well done. Let's do this again for a different initial distribution. Let's assume we have a 0.5 in this cell and a 0.5 in this cell. And remember that this is a cyclic motion model. So whatever falls off on the right side, you'll find on the left side. Can you again, for U equals 2, fill in the posterior distribution? And this is a pretty tricky question, which I'm going to answer in 2 phases. Let's just look at the 0.5 over here. 0.8 of that, which is 0.4, ends up over here. And 0.1 of this, which is 0.05, ends up over here. And the reason why I write it so small is because this is not the correct answer quite yet. Let's look at the other 0.5. 0.4 goes 2 steps, 1, 2, ends up over here on the left side. But 0.1 falls short, makes a 0.5 over here, and 0.05 in the second grid cell. And interestingly enough, for the cell on the right side, there's 2 possible ways we could have gotten there. Either by overshooting, starting in the second cell, or undershooting, starting in the right cell. So the total probability over here is the sum of these 2 things, 0.1. So this is the final answer, 0.4, 0.05, 0.05, 0.4, and 0.1. Let me give you a final example in which I assume a uniform distribution, and I want you to fill in for me the distribution after motion. The answer, as it turns out, will be just 0.2 everywhere, and the reason is, with every grid cell being equally likely, applying this motion model will still make each grid cell equally likely. So let's pick one of them, say this one over here. We could have arrived here in 3 different ways. Perhaps we started in x2 and our motion went well. This gives us a 0.2 times the 0.8. Perhaps we started in x1 and we overshot, which gives us a 0.2 for the cell x1 times a 0.1 for overshooting. Or perhaps we started in x3 and we undershot, which gives us 0.2 times 0.1. When we add those up, then we find that it's the same as 0.2 times 1, because the factors over here add up exactly to 1, which makes 0.2. And the result is 0.2. You can apply the same logic to all the other cells. This guy over here could have come from this guy, this guy, this guy, where this one is weighted with 0.8 and the other two with 0.1. That's called a convolution. And as we'll see later, there's a very nice way to write this mathematically as something called theorem of total probability. But for the time being, I'd like to program this in. So I'm going to give us a probability exact, 0.8, probability overshoot 0.1, and a probability for undershoot 0.1. And I'd like you to modify the move procedure to accommodate these extra probabilities. And here's one way to implement this. We're going to introduce the auxiliary variable s, which we build up in 3 different steps. We multiply the p-value as before for the exact setup by p-exact. And then we add to it 2 more, multiplied by p-overshot or p-undershot, where we're overshooting by going yet 1 step further than you, or undershooting by cutting it short by 1. And then we add these things up and finally append the sum of those to our output probability q. When we run this, we get, for our example, prior of 0, 1, 0, 0, 0, the answer 0, 0.1, 0.8, 0.1, and 0. So here's a question for you that is somewhat involved, and I really want to check your intuition. Suppose we have 5 grid cells as before, with an initial distribution that assigns 1 to the first grid cell and 0 to all of the other ones. And let's assume we do u equals 1, which means with 0.8 chance in each action, we transition 1 to the right. With 0.1 chance, we don't move at all. And with 0.1 chance again, we skip and move 2 steps. And again, let's assume the world is cyclic. So every time I fall off on the right side, I find myself back on the left side. The question is, suppose I run infinitely many motion steps. Then I actually get what's called a limit distribution. So what's going to happen to my robot if it never senses, but executes the action, go 1 to the right, on our little cyclic environment forever? What will be the so-called limit or stationary distribution be in the very end? And you might have guessed it correctly, it's the uniform distribution. And there's an intuitive reasoning behind this. Every time we move, we lose information. That is, in the initial distribution, we know exactly where we are. 1 step in, we have a 0.8 chance, but the 0.8 will fall to something smaller as we move on, 0.64 and so on. The distribution of the absolute least information is the uniform distribution. It has no preference whatsoever. And that's really the result of moving many, many times. There's a way to derive this mathematically, but I can prove a property that's highly related, which is a balance property. Say we take x4, and we'd like to understand how x4 at some time tab t corresponds to the previous time distribution over all these variables. For this to be stationary, it has to be the same. Put differently, the probability of x4 must be the same as 0.8 probability of x2 plus 0.1 probability of x1 plus 0.1 probability of x3. That's exactly the same calculation we did before, where we asked what's the chance of being x4. Well, you might be coming from x2, x1, or x3, and there's these probabilities, 0.8, 0.1, and 0.1, that govern the likelihood you might have been coming from there. Those together must hold true in the limit when things don't move anymore. Now, you might think there's many different ways to solve this, and the 0.2 is just one solution, but it turns out 0.2 is the only solution. So if you plug in 0.2 over here, 0.2 over here, 0.2 over here, we get 1 times 0.2, and that's 0.2 on the right side. So clearly, those 0.2 over here meet the balance that is necessary to define a valid solution in the limit. Now let's go back to our code and move many times. Let's move twice. So please write a piece of code that makes the robot move twice, starting with initial distribution as shown over here. 0, 1, 0, 0, 0. So here's a piece of code that moves twice by the same amount as before. And the output now is a vector that assigns 0.66 as the largest value and not 0.8 anymore. Let's move 1,000 times. Write a piece of code that moves 1,000 steps and gives me the final distribution. So here's my code. We have a loop for 1,000 steps. We move 1,000 times. And we print the corresponding distribution over here. It's 0.2 in each case, as expected. So wow, you've basically programmed the Google self-driving car localization, even though you might not quite know it yet. So let me tell you where we are. We talked about measurement updates, and we talked about motion. And we coded these two routines, sense and move. Now localization is nothing else but the iteration of sense and move. There's an initial belief that is tossed into this loop. If you sense first, it comes to the left side. And then localization cycles through these move, sense, move, sense, move, sense, move, sense, move, sense cycle. And every time the robot moves, it loses information. That's the way it is. That's because robot motion is inaccurate. And every time it senses, it gains information. That is manifest by the fact that after motion, the probability distribution is a little bit flatter and a bit more spread out. And after sensing, it's focused a little bit more. In fact, as a footnote, there's a measure of information called entropy. And here's one of the many ways you can write it. It's the expected log likelihood of the probability of each grid cell. And without going into detail, this is a measure of information that the distribution has. And it can be shown that the update step, the motion step, makes the entropy go down. And the measurement step makes it go up. So you're really losing and gaining information. I would now love to implement this in our code. So in addition to the two measurements we had before, red and green, I'm going to give you two motions. 1 and 1, which means the robot moves right and right again. Can you compute the posterior distribution if the robot first senses red, then moves right by 1, then senses green, then moves right again? And let's start with a uniform prior distribution. And here's the routine. It's very short. It goes through the measurements. It assumes it has as many motions as measurements. It first applies the measurement as before, and then applies the motion. And when it's done with it, it prints the output. And the output is interesting. The world has a green, a red, and a green field. And the robot saw red, followed by a right motion, and then green. And that suggests that it probably started with the highest likelihood in grid cell number 3, which is the rightmost of the two red cells. It saw red correctly. It then moved to the right by 1, saw green correctly, moved right again, and now finds itself most likely in the rightmost cell. This is just looking at these values over here without any probabilistic math and any code implementation. Let's look at the output. 0.2, 0.1, 0.08, 0.16, 0.38. Very correctly, they will most likely assign this position to the rightmost cell, as should be given this sequence of observations over here. Let's pick a different place. Let's assume the robot saw red twice. So it senses red, it moves, it senses red, it moves again. What is the most likely cell? Let's run the program, and we find that the most likely cell is the fourth cell. And that makes sense, because the best match of red to the world is red over here. And after seeing the second red, the robot still moved one to the right, finds itself in the fourth cell, as shown over here. Now I want to celebrate with you the code that you just wrote, which is a piece of software that implements the essence of Google's self-driving cars localization approach. As I said in the beginning, it's absolutely crucial that the car knows exactly where it is relative to the map of its road. And while the road isn't painted green and red, the road has lane markers. And instead of those green and red cells over here, we plug in the color of the lane markings relative to the color of the pavement. And it isn't just one observation per time step, it's an entire field of observations, an entire camera image. But you can do the same with a camera image. So as long as you can correspond a camera image in your model with a camera image in your measurements. And then a piece of code, not much more difficult than what you coded yourself, is responsible for localizing the Google self-driving car. So you just implemented a major function that makes Google's cars drive itself. So I think you should be really happy and proud of yourself. And you should say to yourself, I just implemented localization. Now why on earth does it take Google that long to build a product that drives itself? Well, truth is, the situation is a little bit more difficult. Sometimes roads get paved over and change, and we're working on this. But what you've implemented is the core of Google's self-driving car localization idea. Let me just summarize the essential things we've learned. We learned that localization maintains a function over all possible places where a road might be, where each cell has an associated probability value. The measurement update function, or sense, is nothing else but a product in which we take those probability values and multiply them up or down depending on the exact measurement. Because the product might violate the fact that probabilities add up to 1, it was a product followed by normalization. Motion was a convolution. And this word itself might sound cryptic, but what it really meant is for each possible location after the motion, we reverse engineered the situation and guessed where the word might have come from, and then we added the corresponding probabilities. So something as simple as multiplication and addition solves all of localization, and is the foundation for autonomous driving. I want to spend a few minutes and go over the formal definition of localization. And I'm going to introduce probability and ask you lots of questions. Formally, we define a probability function to be p of x, and it's a value that is bounded below and above by 0 and 1. X often can take multiple values. We had the case of 5 grid cells. Suppose it can only take 2 values. There's only 2 grid cells, x1 and x2. If the probability for x1 is 0.2, what would be the probability for x2? So please enter the number. There's a quiz, obviously. And the answer is 0.8, reason being that probabilities always add up to 1. Let me ask a second question, and I know that's not particularly difficult. What if p of x1 equals 0? And the answer is 1. You got it. For our world with 5 different grid cells, suppose we know that the first 4 of them have a 0.1 probability. What will be the probability of the 5th and final grid cell? And the answer is 0.6. They have to add up to 1. We subtract 4 times 0.1, which is 0.4, gives us 0.6. So that's the valid probability. Let's look into measurements. And they will lead to something called Bayes' rule. You might have heard about Bayes' rule before. It's the most fundamental consideration in probabilistic inference. But the basic rule is really simple. Suppose x is my grid cell and z is my measurement. Then the measurement update seeks to calculate a belief over my location after seeing the measurement. How is this computed? Well, it was really easy to compute in our localization example, and now I'm going to make it a little bit more formal. It turns out Bayes' rule looks like this. And that will likely be a little bit confusing. But what it does is it takes my prior distribution, p of x, and multiplies in the chances of seeing a red or a green tile for every possible location. And out comes, if you just look at the denominator here, the non-normalized posterior distribution we had before. Recognize this. This was our prior. This was our measurement probability. If we do this for all the grid cells, so we put a little index I over here, then just the product of the prior of the grid cell times the measurement probability, which was large if the measurement corresponded to the correct color and small if it corresponded to a false color. That product gave us the non-normalized posterior distribution for the grid cell. You remember this because that's what you programmed. You programmed a product between the prior probability distribution and a number. The normalization is now the constant over here, p of z. Technically, that is the probability of seeing a measurement devoid of any location information. But let's not confuse ourselves. The easiest way to understand what's going on is to realize that this is a function here that assigns to each grid cell a number, and the P of z doesn't have the grid cell as an index. So no matter what grid cell we consider, the P of z is the same. And here's the trick. No matter what P of z is, because the final posterior has to be a probability distribution, by normalizing these non-normalized products over here, we will exactly calculate P of z. Put differently, P of z is the sum over all I of just this product over here. So this makes Bayes' rule really simple. It's a product of our prior distribution with a measurement probability, which we know to be large if the color is correct and small otherwise. We do this and assign it to a so-called non-normalized probability, which I'll do with a little bar over the P. And then I compute the normalizer, which I call alpha, as the sum of all these guys over here. And then I just normalize. So my resulting probability will be 1 over alpha of the non-normalized probability. This is exactly what we did, and this is exactly Bayes' rule. So let me ask you Bayes' rule in a context of a completely different example to see if you understand how to apply Bayes' rule. This time it's about cancer testing. And it's an example that is commonly studied in statistics classes. Suppose there exists a certain type of cancer, but the cancer is rare. Only 1 in 1,000 people has the cancer, whereas 999 in 1,000 people don't have it. It's illustrated by the probability of cancer and the probability of not cancer. Suppose we have a test, and the test can come up positive or negative. The probability that the test triggers positive if I have cancer is 0.8, and the probability that the test comes out positive given that I'm cancer-free is only 0.1. So clearly the test has a strong correlation to whether I have cancer. Here's a really difficult question. Can you compute for me the probability of cancer given that I just received a positive test? Let me emphasize this is not an easy question, but you should be able, based on what I taught you, to calculate this result. Think of the cancer, non-cancer as the robot position, and think of the positive as whether the color draw observed is the correct one. And the answer is 0.0079. In other words, there's only a 0.79% chance, 0.79 out of 100, that despite the positive test result, that you have cancer. And we're going to apply the exact same mechanics as we did before. The result of Bayes' rule, non-normalized, of C given pos, is simply the product of my prior probability, 0.001, times 0.8, which is the probability of a positive result in the cancer state. And that ends up to be 0.0008. The non-normalized probability for the opposite event, the non-cancerous event, given a positive test, is 0.999 times 0.1. And that is obviously 0.0999. Our normalizer is the sum of both of those, which is 0.1007. Just add these two values up over here. So dividing 0.08, the non-normalized probability, by 0.1007 gives us 0.079. We just applied Bayes' rule to compute a really involved probability of having cancer after seeing a test result. So let's look at motion, which will turn out to be something we will call total probability. You remember that we cared about a grid cell xi, and we asked what is the chances of being xi after forward motion. Now to indicate the after and before, let me add a time index. So t, up here, is an index for time. And I write it upper caps so there's no confusion with the index I, which is the grid cell. You might remember the way we computed this was by looking at all the grid cells that could have come from one time step earlier, indexed here by j. We looked at the prior probability of those grid cells at time t minus 1, and we multiplied it with the probability that our motion command would carry us from xj to xi. That's written as a conditional distribution as follows. So this was exactly what we implemented. If there was our grid cells over here, and we asked one time step later about a specific grid cell over here, we would combine 0.8 from over here, 0.1 from over here, and 0.1 from over here into the probability of this grid cell. It's the same formula as here. This is now xi. And the way we find the posterior probability for xi is to go through all possible places from which we could have come, all the different j's, look at the prior probabilities, multiplied by the probability that I transition from j to I given my motion command, which in this case is go 1 to the right side. Now in probability terms, people often write it as follows. P of A equals sum over all B, P of A given B times P of B. This is just the way you'd find it in textbooks, and you can see directly the correspondence of A as a place I at time t, and all the different B's as the possible prior locations. That is often called the theorem of total probability. And the operation of a weighted sum over other variables is often called a convolution. Let me test total probability in a quiz. Suppose I flip a coin, and the coin can have tails or heads. And suppose it's a fair coin. So probability of tail or of heads is both a half. Now let's say the coin comes up tail. Then I just accept and don't do anything. But suppose it comes out heads. Then I flip it again. And after one flip, I accept the result. So my quiz for you is, what is the probability that the final result is heads? And that's an example of total probability. And the answer is a quarter. It's easy to see that the probability of heads in step 2 is the probability of heads in step 2 conditioned on heads in step 1 times probability of heads in 1 plus, that's the sum, probability of heads in step 2 given we had tail in step 1 times probability of tail in step 1. And now the way I set it up, those things here are equally likely. However, if we did have tail in step 1, we would never toss the coin again and just accept it. So it's impossible that in step 2 I flip over to head. That's probably 0. Whereas if I found head, I would flip again, and then the 0.5 chance I arrive at head. If I look at this, then this all becomes 0, and these guys multiply to a quarter, and the final answer is a quarter. Let me make a final quiz, in which I have a coin whose probability I don't know. So there's multiple coins. One is fair, and one is loaded. The fair coin has a probability of heads of 0.5. The loaded coin has a probability of heads of 0.1. Here's what I'm going to do. I'm going to grab a random coin with 50% chance. So the fair coin will be chosen with 50% chance, and the loaded coin will be chosen with 50% chance. But I don't know which one it is. I flip it, and I observe heads. What's the probability that the coin I hold in my hand is fair? Apply anything you've learned before. One of the rules you've learned before is exactly the right one to apply here. And let's work this out. What I'm really asking is the probability of a fair coin, F, given that I observed H. This has nothing to do with total probability and all with Bayes' rule because I'm talking about observations. The non-normalized probability according to Bayes' rule is obtained as follows. The probability of observing H for the fair coin is 0.5, and the probability of having grabbed the fair coin was 0.5 as well. The non-normalized probability of not F given H, which is the loaded coin, is probability of H given not F, which we know to be 0.1, that's the one over here, times the probability of not picking a fair coin, which is 0.5, ends up to be 0.05. When we now normalize, we get alpha equals 0.25 plus 0.05, which is 0.3. If we now normalize the 0.25 over here with a 0.3, we get 0.833, which is the same as 5 divided by 6. So it's our posterior probability we hold the fair coin after we observed H.